So last time we have learned some techniques that we're going to know how to convert from business requirements or business requirement specification to truth table, then from truth table to Boolean equation. Then from Boolean equation, we also learn Boolean algebra to minimize that Boolean equation before wiring. This time we're going to apply specifically into designing arithmetic circuits. It's going to produce more complicated circuit. And if you learn this one, you'll learn how computer performs its computation. Specifically, we're going to learn half adder, full adder, and carry reaper adder. How to design them using digital design. Okay. Now, the first one over here is called the half adder or 1-bit adder. So why is that called half? Because when we add a bit with another bit, it's going to produce a sum and a carry. But it is called a half because it doesn't care about the carry that may come from the previous bit. Okay. So now this one is the requirement specification, or the business requirement that we need to do is binary addition. And we have a bit A, we add it with a bit B, and we're going to produce a sum S, and it may also produce a carry, but we do not care about the carry in. It does have the carry out, but not the carry in right now. Now we have 0 plus 0 is 0, so it's going to bring us 0 and carry 0. And if you have 0 plus 1 equal to 1, and it's gonna bring carry of 0. 1 plus 0 is also 1, but no carry. Next one is 1 plus 1 is gonna produce us 0 with carry 1. Okay, for the next position. So we do have the carry out. Then from this requirements, we need to build the truth table with the input is A and B. The output is the sum and the carry. So we need to rearrange this into a table with input is A, B, and output is sum and carry out. So just rearrange them into truth tables this way. We have A as the input, B as the input, S is the first output, CO is another output. Okay, so let's say if A is 0, B is 0, it's gonna produce 0 as the sum and 0 as the output. So this line is the same as this. So A is 0, B is 0, produce 0 as sum and 0 as carry. Similarly, second round is actually this. A is 0, B is 1, it's going to produce 1 for the sum and 0 for the carry. So that is the second round. Similar, we bring this and that to here. You have that truth table. Now from the truth table, we're going to produce the optimized Boolean equations. How can we produce this one? We're going to just simply use the operator definition. If the truth table or the output is simple enough, it's just one logic operator is going to help us to produce the result, then we should do that. Otherwise, we may apply the product of sums or sum of product to generate the Boolean equation. And after having the Boolean equation, we should apply the Boolean algebra in order to produce the minimal or simplified Boolean equation. Or we can also apply K-map over here. Okay. And in this case, we just simply apply the operator definition. We'll have S over here, and AB as the input, S is the output. So let's look at this one. Okay, S is true only if A and B are different, and that one is by definition or the exclusive OR operator. So we'll now have S equal to exclusive OR over here between A and B. Very similarly, we'll see C is the output and A and B are the input, and C is true only when A and B is true. And this is the definition of the AND operator. That's why we convert it to AND over here. Okay? And these two are minimal already. We cannot simplify them anymore. So we are ready to do the circuit design or wire our circuit. And for this one, okay, we're going to replace the we're going to just rearrange the input and the output a little bit. So we're going to have the input as A and B, and the output is the sums and the carry out. So the input now are going to be replaced with this notation, visual notation, and this notation is called for input pins. Okay. Similarly, we're going to replace the output, which is the sum and the carry out, with other types of pins that you can see from here, and that notation is for the output pins. Okay. Then we still have the exclusive OR operators and the AND operators over here. We'll just replace them with logic gates. So this is the logic gate for the AND operator. This is the logic gate for exclusive OR operator. Now we wire the inputs in. Okay, we just wire the input in, then produce the corresponding output. Okay, so CR is the AND between A and B, and S is the exclusive OR between A and B. Just wire them, then produce the output. Okay. So we are ready for this one in order to produce the half adder. However, if we give this complicated thing to people to use it, it's gonna be difficult to use, and people wanna just use a half adder. I want a half adder, and lots of them do not need to know too much of the details inside. For example, if you wanna use this keyboard, let's say, and you do not need to know the details of the circuit inside it. You only need to know the outside of it. You just grab all the circuit inside here with a box, and tell user what does it do, what input does it take, what does it gonna produce as output, and that's it. Do not provide them the whole details of the circuit inside. Okay, so similar in this one, we are going to do this kind, which is we are going to just move to one more step, which is called the abstraction. So we abstract the details of the circuit into one higher level by grabbing them with some visual notation. Grab them, just like grab a box around this, the circuit detail of this. Okay. Then we also give the input-output specification by describing what is the input and what is the corresponding output is going to provide. And then give also the timing specification, which is how long does it take to go from the input to the output. Okay. And this one is called abstraction. We abstract away the details of the circuit by here we're going to just provide this graph around that one visual notation, okay, and give the functional specification, which is input output specification, and also timing specification. Then let the people use it in the future. They do not need to know the circuit details anymore. So we need to provide what is called appearance or visual notation or abstraction process. So from here on, later on, if people wanna use the half adder, they're going to just use this. Okay, you do not need to see this, just use this. Okay, then we can again distribute or reuse this circuit based on its input output specification or based on its timing specification, and again do not need to know the circuit details. So this one is a whole life cycle of the circuit design. You start with business requirements. You're going to be able to build the truth table, convert into Boolean equation, minimize it. You do the circuit design, but it's too much of the details. Then you're going to move it into the other one. Okay, you'll move into the abstraction level by grabbing here. And then now you can distribute this outside. Okay. In the next part, we'll continue with the for adder. How if we add, but we still need to take the carry from the previous bit. So this is the summary or the half adder that we have seen so far. And this time, if you like to, you should open Logisim and perform the half adder for 1-bit adder like this. And this one is the circuit design, the input gates, input pins, the output pins, the AND gates, and the exclusive OR gate. And in order to edit this, you're going to edit it appearance. So this one is the circuit, and this one is appearance for the abstraction level. Okay.